Good afternoon. My name is FrédérIc PomIes and I'm working for the Excel composite company. So I'll be presenting today two main parts in my here. So the first part is more about the company itself and what we do in terms of composite raw material. And the second part will be focusing more on a product which is related to the wind and marine industry, a prepreg, one of our latest addition to our focus product range. So first of all, who is Excel? So Excel is, before anything, a raw material supplier. We have the entire portfolio of materials that goes into the composite material sector, from the fiber until the prepregs. And we are leading most of these markets with our products there. So we have built over the years excellent customers relationships and also to reach the point where today we are at, last year actually we were reaching $2 billion sales with the split that you see here between commercial aerospace, space and defense and industrial. So this is actually already outdated since this week, as we have announced the acquisition of a new company called Structil in France. So it's up to 20, plus the two more in construction, one in Casablanca in Morocco, and the 22nd one will be our new fiber facility in Lyon area in France. So overall, we are more than 6,200 people now. Next year will be our 70th years anniversary in business, when it all started in 1948, where we invented the honeycombs, the hexagonal cell honeycombs. Hence the name of the company. Excel means hexagonal cell, for those who didn't know. As I said, you know, three main parts in our businesses. The first and most important is in commercial aerospace, where we have a business with Airbus and Boeing into the engines as well, nacelles, and either for business or regional type of businesses there in space, in aerospace. So space and defense as well for the rotorcraft, the military aircraft, launch vehicles and satellites. And where I will spend more time today is on the industrial side, where we are servicing markets in wind energy, automotive, and recreation. So there, wind energy is by far the biggest application where we are present today in our industrial part of the business. It's more than 50% of our total sales there in industrial. Then comes the automotive and industrial specialty session. We will spend a little bit more time later on the automotive, where composites are becoming more and more accepted and being used in many cars. And for recreation, tooling and marine as well, you see more and more applications. Some of them have been there for a long time in marine, for example, which were one of the first users of composite materials, in hulls particularly. One of the most simple way of using materials there as well. So these are the three main areas in industrial. We are using mainly our network in order to service and support our customer around the world. And as you can see, from North America into the European side, also South Africa, we have a wide range of distributors, and particularly here we've been enjoying the support and the service of Access more than 20 years ago. We all started that Excel story in Turkey. They have been representing us first for the aerospace, and now more and more will be looking at supporting industrial markets as well with their help. As I was saying as an introduction, really what our proposal to our customers are really based on the fact that we are able to bring the entire portfolio, from the fibers, and even, we're doing our own monomer, our own PN monomer, going to the carbon fiber that we make ourselves, reinforcement, both multi-axials and woven, going into the prepregs in many of our companies there. We have the resin part of it, the film resins, going to the prepregs as well. And as a separate product line, we do have an honeycomb core, both in aluminum and Nomex based, which altogether are being used for structural and structure in aeroplanes and also other structures, industrial structures. Our addition and our semi-finished product sides will be in what we call engineer cores, where we are able to actually cut to various angles all of our engineer cores and apply as well the prepregs. As I was saying, wind energy, a big part of our business in our industrial, where lightweight, stiffness and strength are the key because of the size of these blades today becoming bigger and bigger. So there, depending on the technology, you would be using either the prepreg type of product. So this one, I will not spend too much time on it because that's the part of the second part of my presentation. But just a word to say that it could be either UD carbon prepregs or based on UD or multi-axial glass prepregs, which more going into the shell and root end application. Once again, I'll spend more time later on that part. Depending on the technology that you might want to use, there is also the possibility to utilize non-crimp fabric, multi-axials, as also called, which are used and optimized for infusion properties. So there we have both carbon and glass that are being used in those applications. And for certain part of where the stiffness needs to be enhanced, needs to be reinforced, we have also some products that we introduced last year, which is a sort of pultruded elements that will be used as a stiffener in the spar elements whenever you need even more stiffness than the carbon structure can bring to you. So that's also a possibility when also going into larger and larger blades. For the automotive, as I said, it's becoming more and more a topic into this, and that has been for a long time actually. We have decades of experience there. We have also looked into the requirements in terms of quality, the ISO TS specification that is needed for the plants in order to be able to sell to the BMW, Audis, etc. And of course, proposing a diversified product portfolio that would bring both the structural part, the safety part, but also the appearance itself is something important for the automotive industry. And when you see at the three main parts where composites would be used and has been used for some times is of course the body parts and the carbon look parts, which are today into the minds of everybody for composite and maybe high-end type of car, where you would be using either fabrics if you are in the infusion side of the business, or directly the peel ply. But, and most importantly, the structural part and the chassis of the cars are more and more being considered for being used with composite. And I will just invite you to stop by and look at the video we have on the ASES stand, where we are presenting the stacking and the B-pillar project that we have had with BMW, where actually the idea was to lighten the B-pillar structure and with a stack of composite with some film adhesive on the metallic part, we've been able to lighten the structure of the material. Last but not least, our industrial specialties applications. Historically, we've been present for a long time in winter sports. I would say 80% of the skis around the world are being made with our materials, prepregs, polyurethanes, and of course the laminates that comes with it. But it's not only that, we are also present in the bike and sports and leisure, marine, and all the industrial other applications that are many, many, as we can see even in that exhibition today. Just a small words about sports and leisure first. There also the carbon look might be of importance, where you will need to have really the parts that would look nice with this black carbon type of material, where spread fabrics, that's the prime text fabrics that we are proposing to our customers. It's a way of better coverage of your fabric, which would actually also enable you to use a higher K for a lower weight. So for example, you'll be able to make 100 grams materials with a 3K instead of a 1K. So of course, this has a lot of interesting qualities, and particularly the fact that it will cost less because it's a 3K versus a 1K. We do use, as I said, the cores and the adhesive in that business as well. It's not so anecdotal, but the little representation of a surfboard there is also to say that we do sell our surf fabrics, glass fabrics, into this world, and actually we estimate that more than 100,000 surfboards are being made with our fabrics every year. So we have 1/3 approximately of the total market there. And we've been there also for quite a while. And the structural components in bikes, for the bike wheels, for the frames, and also for these sport elements where you need structural. This is important to work with all the various prepregs and elements there. In order to finish on the industrial side and the general presentation, we have also a range of fabric for marine that enables us to service the industry both for structure and also for the rigging. So more and more you see that in multi-catamarans, but not only. You will see that in super yachts, where carbon and glass, multi-axial, woven fabrics, and more prepregs are being used for their structural properties. And there, the interesting thing is that if you are building carbon masts, you will need intermediate modulus and even high modulus fibers in order to be able to sustain all the mechanical requirements of those masts. All of this is being done, of course, with lots of investments in innovation. So the latest one was installed in Duxford, UK last year. But we have one in every plant, basically one in Leicester in the UK, in our multi-axial plant, and one in Neumarkt in Austria, where wind energy, automotive, and recreation applications are being developed. Really, where we see the industry going is more and more fast curing resins for prepregs, low temperature cure prepreg. This is really what I will insist on in the next slides. Polyurethane and pultrusion technology, that's also for reinforcements. Tooling materials as well. We see a real move towards composite tooling materials from basic prepregs until more complex material like our X tool, which can be remachined afterwards. And last but not least, the adhesive that enables you to stick basically any kind of structure into a composite structure, into a different material like steel, for example. So this was the general presentation. I will be a little bit more going into the more technical details about this new low temperature cure prepreg that we have developed for wind blades and marine structure. So this is I would say a typical schematic of wind turbine blades, very simplified of course, but to introduce that schematic, we see a drive towards more and more larger blades in order to extract the most from the wind. We see them on TV, we see them more and more, these blades when they are being transported from one part of the countries to another. But really, the materials that are needed for this type of blades needs to be developed and needs to be adapted to those new challenges. And of course, there are two types of processing for blades today. One is infusion, the other one is pre-preg technology. Overall, inside the structure, you will see the load-carrying elements. And that will, because of the increased dimensions, these load-carrying elements will ask for carbon more and more, again, because of the mechanical properties that are needed, and for higher modulus of the structure itself. As I said, the material processing itself depends on the philosophy of the manufacturer. It can be either infusion or pre-preg. But in certain part of the structure, like the root end, where there is much thicker parts, you will need to go into glass composites, and the fact of having a very thick part, there is also a risk of heat buildup. So that's something that in the case of standard pre-preg was not overcome until recently. So overall, the benefits of pre-pregs are known. Cycle time are half of those of liquid resin infusion, but it can be more difficult if actually you have to lay up more plies, and if it takes, if at the end of the day you have to cure at a higher temperature. So looking at that, we see really a drive towards lower temperature cure. Typical curing temperature in wind energy components is 120 degrees Celsius for the traditional pre-pregs. Of course, resin infusion is cured at a lower temperature than that. So we needed to be able to develop a new material in order to compete with those kind of processing. What we saw in the old system, the M9 system, is that it was requiring what we call a dwell phase. In other words, you need to go up a little bit in temperature before you can go to the 120 degrees Celsius temperature. And there is always a risk of exotherm, and that could lead, of course, to a damaging of the part and the parts beside it. So, and of course, the fact that you need dwell time, that is a longer curing cycle, you will have a longer build rates at the end of the day. Outlife is also a very big challenge, because you want your pre-preg to be able to be used even at places where the customers would not necessarily have a frozen chamber in order to keep your pre-pregs. So you want the outlife to be as long as possible at room temperature. So thick structure can be quite, some of them can be quite heavy. We've developed that concept to the limit of the number of plies that could be applied. I come back into those kind of thick structures. Today, I would say the maximum number of plies that are being found in wind is around 100 plies, which is already quite a challenge. So with the latest generation of these low temperature cure pre-pregs, the shorter lead time, and that's also an addition, will lead to higher throughput. Therefore, and that's also very important, the molds that you are going to use are not occupied so long and could last longer. So you have a choice, a compromise between either using lower cost material for making your molds, or you can use the existing molds for a longer period of time because they're being used at a lower temperature. One important thing that is also there is the fact that you can co-cure with infusion because of the temperature being at the same level. As I said, infusion being done at 70, 80 degrees Celsius, with this kind of pre-preg system, you would also be able to do it in out-of-autoclave type of production, and that would be done with co-curing with infusion as well. Finally, one thing important, and we'll come back to that as well, the fact that you want to avoid any air trapped, you want to avoid any problem on the porosity of the final curing, because who says porosity is of course related to the fact that you will have weakness point in your very thick structure. So that's also something we've taken care of by applying to each and every ply of our prepreg what we call a grid technology, which takes all the air off and enables the porosity to be at the lowest possible level. Here is an illustration of how prepreg technology can be compared with the typical liquid resin infusion systems. And in order to do that, we've measured what we call the exotherm, which is actually the potential amount of energy that is available within the system in order to generate heat. So originally, the liquid resin infusion systems have exotherm potential, which are relatively high. And the classic prepreg systems, when they were started, they were exactly at the same level than this LRI. They went down to a certain level, but it was still not enough. So the real breakthrough was the reduction of this exotherm possibility down to 150 average. In certain processing conditions, you can even go to 100 joules per gram, which is really also a very big advantage in that particular case. And as you can see, Outlife, we've been able now to offer up to 6 weeks at room temperature. In other words, these kind of materials can be kept 18 months or even more at minus 18, 6 months at 5 degrees, or 6 weeks, up to 6 weeks in the room temperature, 23 degrees Celsius. So that's really an advantage. Of course, we're not there yet at the liquid resin infusion side, but it's really mainly due to the fact that liquid resin infusion, you will mix 2 components, and this, of course, you can use it anytime you want. But that remains for us a challenge to continue offering prepregs with a higher and higher outlife. Here is also a way to illustrate the difference between standard prepregs and low cure temperature prepregs. This would be a cure cycle, very, I would say, simplified for a typical standard prepreg. So you can see the dwell time first, around 60, 70 degrees Celsius, before you go to the 120 degrees Celsius cure temperature that you need in the case of this type of prepreg. Why do you do the dwell time? Is again, if you were to go too quickly to the 120 degrees Celsius, you would have a risk to generate heat buildup and then getting that exotherm that you want to avoid by all means. What is interesting about the new system is the fact that with a fast ramp rate, heat up ramp rate, you can go up to the low temperature cure that we have defined as a minimum, 70 to 80 degrees Celsius, but you can go there immediately without having this dwell time. The only time where you would need maybe a dwell time would be if you really make very, very thick part, because just again to avoid and to have to be sure that the heat will be all over the parts that you are making. So really that's the main difference. This way the risk of exotherm is reduced, and of course you have less need to monitor very closely your thick parts in order to get what you need. To push that to the limit, we made it with nearly 700 plies of of carbon UD 600 material. So a huge, a big cube that we call it. We call it the cube experiment. If you stop by at our booth, you will see a slice of it, which has already 120 plies, and you will see how heavy it is and the look of it. But this one was to really push that to the very limit. And we, of course, it's not realistic for what it is being made today. But it's also to demonstrate that if you can do it with 700 plies, a less thick or thinner material would be, of course, more easy to do at the same time. One thing to notice also is that we really also used our air vent grid layer facility layer, which helps, again, getting rid of all the air porosity. On the left side, this is the cure cycle that we used, and as you can see, there is indeed, because of the thickness of this cube, there is a little dwell time that we did between 60 and 70 degrees Celsius. This system is, of course, quite reactive, and if you go too slowly into the curing temperature, you have the risk of also starting up the reaction, and then the flow itself will not be, the resin flow will not happen. So that really, and you see, for such a solid part, for such a thick part, the maximum exotherm that was measured was 140, which is really, really remarkable comparatively to what we are used to. On the right side, it's just to say that within actually 8 hours, we calculated that the material was fully cured. So these big cubes was fully cured in 8 hours in order to, and then could theoretically be removed from the mold. So again, it's an extreme type of experiment, but showing that thick part can really be made with that kind of material. As a conclusion on this experiment, you see that it's possible then to build multi-layer of carbon and make a very thick part. And this is nearly close to monolithic. Again, you will see on our booth how monolithic it can look. And also, very remarkable is the porosity level that we could measure there, which is much lower than 0.5%. So really, practically no porosity, and the porosity even was not a critical one. We apply all that knowledge into the marine environment as well. And in the marine environment, we are working with some shipyards that are building racing boats, the maxi catamarans, the ultimate catamarans that we see going all over the world, 45 days to go all over the world. And there they have really big challenges in terms of curing, processability. They cannot go too high in temperature because of these thick parts, unique parts. Then they want to avoid any exotherm because there is so much parts around and you don't want to damage them at all. The core, for example, and all the other parts. And last but not least, the structural part of it, because these boats need very high structural properties, and that's why here we used IM fibers, intermediate modulus fibers, much higher modulus fiber than the normal fiber being used. At the same time, we also see that porosity, which can be a weak point into the structure, is related to the process that you will be using, but also the curing cycle and the auxiliary materials, auxiliary way of making your material. And just to illustrate that, as a benchmark, we used what our customer was proposing as a curing time. In other words, it was a curing cycle. He had some debulking in there, and this curing cycle led to a 1.3% porosity. Of course, we know that, and he was not using any air vent technology, air vent grid, in order to get rid of the air trapped, the trapped air. So we can see here, so depending on the auxiliary materials, depending on the cure cycles, if you use or not the scream in order to get rid of the air, you are reaching different type of porosity levels. But again, as you can see on the photographs, for some of this porosity, every time it's black, it's actually a porosity. They are not all of them at the same locations. And the criticality of porosity is, of course, related to the fact if it is interlaminar or intralaminar, it will be much more critical on one side or another. So it is important to say that at the end of the day, the finished product quality will depend on a number of factors that you will be using during your curing. The auxiliary materials, do you use, yes or no, the screens to improve the air evacuation? Also the fact of you are going to debulk, yes or no. Some companies will debulk systematically every single ply. In that case, it was 30 plies. But it's a lot of work. It's a lot of time spent. If you were using only the grid, then that, of course, goes much quicker. The geometry of the part, the distance, that will influence, of course, the air evacuation. And the cure conditions might also change the porosity values. When we started that experiment with that customer, we noticed that they had a ramp up of the heat was too slow. And of course, they were starting to cure the materials too early comparatively to what we had suggested. We could improve the heat up rate, and then it could really help them getting to the level where they wanted. As a summary for the M79 and a wrap-up, low temperature, low pressure cure is really a drive in the industry that we see not only in wind energy, but in marine, in automotive transportation, for industrial machinery and in sport equipments. This is really something coming more and more. Even agricultural parts, we see beams, bombs also that are being used a lot in agriculture, where composite is needed because of the span lanes that you will need on your, it's like a mast basically. So the fact of having flexible cure, 70 to 100 degrees Celsius, help in getting out of autoclave processing. You can cure, I tried to demonstrate that you can cure 6 surfaces. Again, stop by and see us. This part is really worth just taking a look at. Reducing the exotherm, less risk of hotspots, of core damages, and the possibility to use co-curing. And at the end of the day, the outlife is still an improvement, but you can use as well either with glass or carbon UD or IM fibers. That's really a very flexible, a very versatile type of prepreg. Just to illustrate the fact as a final conclusion that we continue to look at the composite markets as a raw material supplier and a demand on the wind energy, the automotive, recreation, marine and industrial specialties. And maybe there will be a day where actually automotive is getting to a point where aerospace is today. And this is something that is becoming, and there also lightweight structural properties will be needed. So again, thanks a lot for your attention. Thanks to our distributor Access to welcome us here, and thank you for your attention.